Hi guys, I'm Chao, and today I'm going to talk about using machine learning to build intrusion detector and from attacking data. So, it has been a very long war between the attacker and the defender. So the hacker they usually use different kind of like master to attack. The defender with laptop. And for the defender, they also need to like improve their skill to know like how to protect those kind of attacks. And basically now there are four main categories of the attack types: DOS, R2L, U2R, and prop. So in this problem, I'm trying to build in the machine learning models to detect the potential attack based on the features. So the data we use at here is KDB Cup 1999. And although it's a little bit old, but we also can learn a lot from this data set. And if we could know like the potential attack events, then we can know that how to block those. Block those requests if they are suspicious. And also like if we found something like it is like abnormal, we also can terminate the service. So the framework is like this. So first, I will do the data exploration and modeling and then analysis. And for the data set we use like 41 features and one response variable. So basically, there are three main types, and I will introduce them later. And for the response variable, we basically have like one normal class and 23 different attack type informant categories. So the thing is that we just mentioned. So as you can see, like these only have not just have like a main category, you only have like subtype. So it's like MDOS, you get like Neptune or Land or Pod, and also for the other classes. So the total number of training data here is around like 5 millions, and the testing data is around like 300,000. Uh, so, the features we get from dataset is like this. So basically, we have like basic features of individual TCP connection. This including like durations, because like duration is very important because like if you have very short duration, which means that you might just send a lot of like different kind of attack in very short time to try to paralyze the server. So those features are very important. Also, like from the source type, which is like a number of data bytes from source to destination, is also important. So if you send a large number of data, bytes, then this might be kind of attack. And they also have like content features with a connection by domain knowledge, and also for traffic features, computer user tool taken time window. So anyway, we have like a lot of like 40, around like 40 features and 41 features, and then we were trying to use this to build a model. So the first thing is that we have to do some exploration of the data. The first problem I saw at here is that the training data set is too large and very time consuming for building models. Why is that? Because like we get around like 5 million models. If we just 5 million training data, if we don't do anything on it, it takes a lot of time building a model, because if you only use like single machine instead of like a lot of nodes, it takes a lot of time. So one of the best way is to just take a sampling from it. The take sampling is that you can increase the speed of processing and also keep some property or characteristic of the original data. But it's better like after you're taking the sampling from you use it to building model. Finally, if you decide what kind of model you want to use, it's better to just train off the data again, using all of the original data. And the second problem is that there's other like many duplicate rows in both training data and testing data set. So the solution for it is very easy. Just remove the duplicates. So we have only total number of training data will be around like 145,000, and the testing data is around like 77,000. So let's take a look at the distribution of training data. So the distribution is that around 40% of data are abnormal. And the other thing worth to mention is that we have like a kind of type called Neptune. Neptune is like kind of like a tag, and we have around like 36% of Neptune. So which means that this data set is just very skewed. I mean, the distribution of classifiable is very skewed. So this is a part we have to take care of. So now I'm going to talk about the modeling part. So the modeling part, basically, there are now mainly two categories of models: generative model and discriminative models. So the generative model is that you have learned both the prior probability and also the probability of a feature given the tag types, and to do the inference. And the discriminative model is that you just need to using like the probability of feature given a tag type. So I mean the main difference is that the generative model they assume like a very strong probability. So you are based on the distribution of training data set. So I mean if we can ensure that distribution of training data set and testing data are similar, I mean generative model might be a good idea. So anyways, like in this experiment, in this project, I will use try different type of models and run the experiment and demonstrate the performance. So there's a model I use, and it have like naive Bayes, KN, logistic regression, and decision tree, and random forest. And for a naive Bayes model is like a classifier based on applying like Bayes theorem. So I mean the core idea is that they assume that the features are independent. So as you can see, like we are trying to maximize the likelihood of this function, this equation, and we take a log on it. So because that it can keep like they are just a same, and then you take log on it and remove the constant, which is bottom part, so you can get the equation like taking like this. So you are trying to maximize this, but as you can see, this will cause some problem because the probability of feature given a tag type may be 0, so you cannot take log 0, so you need to do some smoothing. And okay, so this is like the R implementation for naive Bayes, and as you can see, like didn't have any very complicated structure, and the parameter that we had here is called threshold. So it's like the one we mentioned is like about how to try to do some smoothing. So it's like a value placing itself with a 0 probability. And so from this slide we can see like there's like some threshold right here. I mean you can see based on the x-axis is the threshold. So you can see like when you increase the value in threshold, the performance is, accuracy seems like a little bit increase, and then go up and go down and go up. So it's like you can find that when we have like the threshold equals 0.5, we have like the highest accuracy. However, compare this with the other models, it's actually had like a bad, worse performance. But why is that? So I would like to try to discuss about this. So the first thing I found is that about the distribution of the training and testing data set. So you can find that they are fairly different. What do I mean? It's like you can see the training data I just mentioned is around like 40% is like normal, and when we take a look at the testing data set, well, it's also around like 40%. However, now we have like we have increased a large number in the others part. So there's like another much more abnormal sample in this part. So now I mean, the distribution are very similar, a little bit like I would not say like very, not very similar, but I mean like they're just a little bit some difference. So this one we have to think about why maybe this might that the night base fell. And the other thing I want to mention is that because the night base have an assumption that the features need to be independent. Um, but I mean, when I trying to reduce the correlation matrix, as you see at here, we can find that there's like a lot of features are not correlated. I mean, they are highly correlated. So as you can see, like the size of the circle is depends on like if there are like high correlation. So we can see like a lot of blue type, and the blue color is like they have a positive correlation, and the red one is like they have negative correlation. So we can see like there's a lot of correlation, and so this might be dissatisfied assumption from night base. So then I'm talking about like logistic regression. So for logistic regressions, basically we are trying to minimize the cost function, as you can see in the first equation. So we are trying to learning the data for each attack type. And also we need to see like, because I mean if we just use those kind of cost function, it will let us to overfit. So for avoiding overfitting, so we can do some realization on it and taking like a lambda. And because like the cost function is very uh, difficult to, I mean, to get the minimize of it. So we also usually we will use to take the gradient descent for implementation. So gradient descent is like you just go down by the slope. So just depends on the step size, and then finally we'll get a local minimum. But you know, it is about the local minimum. So you also need to take care about like if you are finding. I mean, it's better for you to just try the experiment for several times. And the implementation is like this. And one of the package I use is GLMNET. So I mean, I tried a lot of different logistic regression package, but I found this one is much more very useful because like it didn't require you to put any parameter on it because it will help you to find the lambda by automatically. And okay, so that's the result of the logistic regression. As you can see, the absolute value of the accuracy is better than the naive base. And you can see we cannot have like lambda too large, it will decrease the accuracy. And the other way I do it, I build a model is using KN. And KN is like very useful model, and you just need to find the top k nearest neighbors. For example, in this graph, we can see like if you want to predict the testing sample, we just take the similarity. We can use like Euclidean or also use sentiment, depends on you. But I mean, it is just find the top closest the sample in the training data set, and to see what the class that they delay belong. So for example, if we have k equals 1, we can find the green triangle is very closest to testing sample, so we have like assigned it to an action. So if k equals 3, you can see like there's like two normal square which are blue, is much more closer than the other points. So and also I have origin or Neptune. So because like there are two normal here, so you can see both them as a normal. So I mean, k is like the parameter is that the k is the number of neighbor we need to consider, and we can see like k has a very good performance, but it also decreases when you increase the number of k, and I want to discuss this a little bit. So why is that the accuracy for KN keep dropping? So one of the possible reasons is that because the screw of the distribution. As you can see in the graph on the bottom left, and there's like number of unique attack type in prediction, So I mean, when we increase the number of k, because it's very much more difficult to assign the label to a class label to the testing, because now you don't have a lot of sample in the training data set. So as you can see, it is almost impossible to assign a label to rootkit. The rootkit only have like 10 sample, but if you have like k equal to 300 and it is although if the point is very closer to many rootkit point, however, if a rootkit only have like 10 sample in the training data set, it's very difficult to assign label on the net testing data, testing sample with rootkit label. So now I'm going to use the decision tree models, and for decision tree model is that it's like a tree-based model for classification. So I mean, when you learn a tree after that, so you just need to put a testing sample in it, then you will just go right and go left, and finally you know what colors it had, and the thing we need to be to be careful is that we need to prune the tree to avoid for overfitting, because if you growing the tree too large or too deep, it's very easy to overfit the results. And the other advantage of the decision tree is that it's very easy to explain, because you know which features are much more important than the others. And the parameter we use at here is called mean spelled. So the mean cell is the minimum number of observations that must exist in a node. So when we have like a large number of like observation in one node with minimum, so you will not. I mean, if the mean spelled is large, we will not have grow a lot. I mean, deep tree will just grow a small tree, and is a result I got. So we can see like when mean spell equals 5, we have it is a minimum. I mean, we have like the best performance among all the other parameter. So this is very interesting. Is that I found that when I did this project, very interesting, because like you're not only like using your domain knowledge to solve the data science problem or machine learning problem, you're also learning from the data. So what do I mean? So let me just share my screen with you. So I mean, so when we have to finish the building the decision tree, we can see like the spell of it. So the first spell is that if it's a percentage of connection to a send service. So if it is less than 0.33, it will go left. If it's 0.33, and go right. So I mean, this figure seems very like makes sense, because like most of the normal user will keep using the same service instead of just change same service like in short time. So I mean, this makes sense, right? So so we can discuss like sequence build for wrong segments, and because most of the normal users will just send only the correct fragment. If it continues to send like wrong fragments, it might be a kind of signal for attacking. So I mean, this is also like an interesting thing you can learn from the data. I mean, found from data. And the second spell for B is also much more important. I mean, much more interesting, because like I would say like, because the class label I'm not familiar with. I'm not like very familiar with the internet security. So they have like Neptune and Saturn type at there, and because I am not familiar with this, so if I can ensure like the decision is correct, I can also learn from the data, so we can know what is the difference of attack between the Neptune and the Saturn. So it is because of like they have different percentage of connection to different hosts. So this like interest is very, very exciting. We can learn from it, and also can do the same thing on almost each spell. So yeah, it's very interesting. And the random forest is the master I try to use, and the random folder is like a very ensemble method to combine several decision tree. So I mean, it can reduce the problem in the decision tree, because if we grow the decision tree too large, it will have very low bias but very high variance. So if we use it in the bagging method, like like we use in the random forest, we can reduce the variance. So the concept is very easy. So we have like several different tree, and we put a testing sample in it, and we just let each different tree to to make a prediction, and just using all the result to voting and to do voting, and then to see like, so for example is that we have like 2 naptron and 1 normal here, so we can predict that it may be a naptron. And because I did the for the random forest, you only use part of the features in each tree. It's normally like the like the square root of the number of features, and we also use some. We also didn't use all of the feature, the sample. We just use part of them. So, I mean, this could help us to reduce the variance from it. So, the implementation here is also not that difficult. So we have to tune the. You have a function called tuneRF. So tuneRF is help you to find the optimal number of features to use in random forest, and then you can apply this the tree you should use from it, and then put it in the random forest function. Okay, so the results I think very excited because it has a very excellent performance comparing with the other the other all of the models. So, but I mean the problem is that it takes a very long time in training. So now I'm going to talk about like parallel computing, because like we want to achieve a better performance. Using a random forest, we could achieve that better performance using a random forest and a decision tree, because this. But I mean, random forest is combining with several decision tree, so that's the reason why it's better. But you know, it also takes much more longer time, because now you don't need not only need to train one decision tree, you need to train a lot. So how about like doing it in parallel? So so I'm trying to do in parallel computing with R. So this is like the package provided by Reversion Analytics for each and how to do project package, and then we try to run parallel merging of random forest. Okay, so the scene will become like this. We have like several mappers, or say several processor, and we let each of the processor mapper to train a different tree. So because like you know training the random forest is like you can it's not sequential. For example, there's some example is like sequential. For example, like stochastic gradient descent. It is sequential because that you need to do the training based on the result, the vector you train in the last part. So I mean, it takes much more. I mean, the process is sequential, so you cannot do it in parallel. However, for random tree, it's not the case. You can train it in parallel, and finally, you will just reduce the results by combining, just like voting, and then you combine the result, so you can see which one is the one to predict. And so for random forest, parallel moment for you can see the graph is like very interesting, because like at first it seems like the parallel random forest is much more slower, because like I think the reason is because of it needs much more like communication cost kind of thing like that. However, when you increase the number of the means belts, the number of trees in that, so you can see now it has like the random forest needs to run very long time. However, the parallel random forest now much more faster. So, I mean, if you if you want to run in like a large number of trees, so it's better just to use like just to use like the parallel version of it. So finally, I will talk about the last part of the framework. It's called analysis, and so I would say like how could we learn from the data? So there's like basic 2 type of data that you can use. So one is descriptive, and the other is inferential statistic. And okay, so this like the very simple descriptive status that I did is like average of, because that the most of the features we have is like the numeric, so we can do like take the average value of it. So I mean, it seems like not a very complicated method, but actually it is very useful. So I just do for because we have like around 40 features, so I do many of them. As I will do all of them, and I'll do an analysis here. And so, what can we learn from this data set? So we can observe that there is like for different kind of characteristics of attack in DOS in different attacks. And for DOS, actually, the common characteristic in a DOS is that it has very short durations. So I mean, this also makes sense because like for DOS, it's like trying to send a lot of like requests in a very short time, try to uh, paralyze your server or break down your server, and so that's the reason like have like short durations. And for each attack event, also have like a special type of attack type. And for example, like backtrack, they send a large number of bytes, and Neptune, they send a large number of requests very short time. So it is like you know very like interesting. We can learn from the what kind of attack type have what kind of features. So in the prop, is like a scanning port. So usually it have very low logging successful rate. So because like you only like want to uh, do some like IP sweeping or port sweeping, so it didn't actually just have like the ability to log in successfully in your server. So you'll just try a lot of different kind of like ways to try to log in, but it's like almost zero. And for example, like for IP sweeping is like there's like high percentage of connection to different hosts because they different hosts have different IP, so just do a lot of IP sweeping. And for R2L is like like a high number of hot indicators. And for individuals characteristic for each type is that, for example, like gaze password, you also have a very high number of failed login. And for I mean, this part is very different from the previous one. The previous one is that the problem is that you have like a very low login successful rate instead of number, so they have a rate of it. And the R2L is like guessing password. Like they trying to have guessing all of them because it's like brute force to guess your password, so you have high number of failed login. So it's not about rate. It's like I mean, it's also rate maybe also low, but I mean it's much more focusing on like high number of file login. And the multi-hop is like have like high number of file creations. And the U2R is like they have a high number of root access because they want to do some unauthorized access to local privilege. Okay, and then this is like a very simple summary of the models. We can see like the random forest racings have the best performance among all of the model I tried. And however, running time is also take longer because like although even if we use the parallel version, I mean the number I put here is like already a parallel version, but it's still very slow because you need to build a lot of tree. For example, if you have like 4 nodes, you still need to, if you want to do like tree equals 500, you also need to build like 125 tree for each node. So I mean, it still takes longer time than like just using a decision tree. So I mean, decision tree only needs to build one, and also like KNE is also very fast. So finally, I want to do some like the key takeaways about to do some model comparison. So we can see like the random forest actually has like the highest accuracy. However, it also has like the highest running time. So if we consider like the accuracy and runtime, I guess like the KN and the tree might be a better choice. And also I want to just mention again that thing we can learn from data. So we have like different attack type in DOS. I mean different characteristics. I mean in prop and R2R and 2R. So each one attack you can find some like interesting character and you're learning from learning from the data, you can know what kind of attack have what kind of characteristic. So the final takeaway is that sometimes we need to do some tricks in reduce time to build model to do. I mean, this part is very important in data science or machine learning because now we have large scale number of data. So if we didn't have a large number of machines, one of the better ways is to sampling from data. However, you also need to be careful. It's like if you're, the data you want to sample is like if there have like the distribution of it, you have to take care about that. And also, you also need to do some data cleaning, and because you want to find out, sometimes the data set has a lot of like, missing value, and also like duplicate one. So just just be careful. You have to remove those kind of things and do data cleaning at first before you build your model. And that's all about my presentation. And thank you.